Okay, again, we're trying to figure out the work done in raising a mass from one position to another relative to the center of the Earth. One position being at 6,350 kilometers, which is, I think there's some place on the surface of the Earth that's that far from the center. And this is 450 kilometers further from the center. Think of an altitude of 450 kilometers, around 300 miles. The gravitational force on any mass that you want to raise, according to this law, is going to depend on the mass of the Earth, the mass of the thing you're raising, and distance from the center of the Earth. And the distance from the center of the Earth is changing. So we can't just use one value for the force exerted by gravity. Now if we want to find the work, we got to, know what force to use. And we don't know what the average force is. We got a simple way of calculating it, but we want to follow the usual standard procedure that we need to learn and set up an integral from this from the first step of partitioning this interval. We know that the thing that we're trying to calculate changes with r. So we have to partition this interval. And here's our partition. R0 is 6,350 kilometers. Rn is 6,800 kilometers. You have some Ri between R0 and Rn, and you have some ith subinterval. And all we have to do to figure out what to integrate is figure out what happens on the ith subinterval. Now the ith subinterval is going to go from r sub I minus 1 to r sub I. So if I is 796, then you go to the 796th number in this partition, and you take the 795th and the 796th, and you choose some value of r between those two. Okay? And that'll be your value r sub I star. That's the value we're going to use to calculate everything within this subinterval. Now, of course, we understand where we're going with this. We understand that we're going to shrink these intervals. We're going to shrink all the intervals down in some uniform manner, so that the variations in the thing that we're trying to calculate, in this case, the thing that we need is the force exerted by gravity on a given interval, so that that thing doesn't change very much. So if we take this partition and use enough intervals and make them all small enough, then we can confine ourselves to intervals of length a millimeter or less, let's say. And we know that wherever we are, the acceleration of gravity, which gives us the force of gravity, doesn't change significantly over a millimeter, at least not very significantly. Not in any way we can measure, don't think. Okay, so we have this idea that we don't care about any other subinterval, we just pick one of them, and whatever we do in this subinterval stands for whatever we would do in any other subinterval. Okay, we have a subinterval that's determined by the partition and a sample point r sub I star in that subinterval, in that ith subinterval. Now I say here, whatever's variable varies negligibly on each subinterval, provided the subinterval is small enough. It's kind of a brief statement of what I just said. Okay. Okay, well, what do we need to find? We're trying to find how much work it takes to get from here to there. So we need to find the work on the ith interval. Okay. Well, the gravitational force is easy to find. So, we just plug in, what? We plug in r, but on this interval, what are we using as a basis for all calculations of the quantity that we're integrating or that we're going to sum up? We use r sub I star, the representative value of r. Doesn't matter where it is in the subinterval. If the interval is small, it'll do. So we plug in r sub I here to get our force. Okay, well, delta Wi equals F sub I dot delta S sub I. Okay, delta S being our displacement and F sub I being our force. Okay, well, F sub I is what? We calculate F sub I based on R sub I. Now this is a vector, so I'm going to use the vector form of the universal gravitational, of Newton's law of universal gravitation. Here is the vector form where I'm using R sub I for all the R's. Okay, here's our unit vector in the direction of the displacement, in the direction of increasing R. I'm in the direction of R, okay, in the direction of R sub I. And here's the magnitude of R sub I, which is squared, and here's everything else. And we dot that with our delta R sub I. Now, delta R sub I being parallel to itself, what we get is not exactly, yeah, okay, it is what I wrote down. A little word there, a word that I'd forgotten, the product of this with the unit vector, but I've got it. Okay, and okay, delta R sub I is parallel to R sub I, so implicitly we've chosen a path parallel to a radial vector from the center of the Earth. Okay, we've chosen our path to be along a radial line, a line directly away from the center of the Earth from this distance to this distance. Now, what we're learning in multivariable calculus right now is about conservative forces and so forth. We did some stuff in lab where we look at the conservative nature of some forces. We could have chosen another path, and from what we know about gravity, we can verify that it is a conservative force, and that even if we didn't go directly along a radial line, we get the same result for the work necessary for the work done against gravity from this distance to this distance. It's independent of the path that we take, which is kind of fortunate in rocket science, and not that I'm a rocket scientist. Didn't go that route, and probably would have been a very good one. Okay, again, because of the conservative nature of the force, it's okay to use a radial line. Any path will do when you have a conservative force. Gravity's conservative, so there we are. Okay, anyhow, we do this dot product, and we get this. Okay, just negative g times big M little m over R sub I squared times delta R sub I. Magnitude of delta R sub I. No vector over that, it's a magnitude. But that leads us to an integral. And we were out of time. I didn't have time to write down the integral. I'm going to go ahead and write it down here. This video is getting a little long, so I'm going to do that in a separate clip.